So welcome everybody to the last IQuist seminar of the semester. We are excited to have Lilian Childress from McGill University joining us today. Lily did her PhD at Harvard with Misha Lukin, and then she went to Bates to teach for a few years. Then she spent a couple of years doing short postdocs at TU Delft and Yale before arriving at McGill, where she's been since 2013. So as usual, please put your questions in the Q&A, and Lily has agreed to try and answer them throughout, so I will interrupt her with questions if you put them in there, and take it away.
Great, thank you so much, Elizabeth. And yes, I have absolutely no need to get through all of my slides. I'm happy to answer questions, no problem. And let's see if I can make this so I can see everything. Great. So thank you very much for the invitation to come at least virtually visit. Today I'll be talking about our efforts to develop a cavity quantum electrodynamics platform suitable for NV centers in Diamond. And while it's a work in progress, I think it's a promising direction, and I'll try to highlight some of the potential benefits as well as the challenges that we've encountered along the way. The motivation for this work comes from the large-scale effort in our community to develop quantum coherent networks, where nodes comprising essentially a small quantum processor can be connected, potentially over long distances, by photonic channels, offering potential solutions for long-distance quantum communication, distributed quantum computing, and enhanced metrology. Among the many physical platforms being pursued, the Nitrogen Vacancy Center in Diamond has recently become a frontrunner, thanks to its long-lived electronic spin, which was recently measured to have a coherence time over a second at cryogenic temperatures. And as it also has the possibility to interact with nearby nuclear spins, which are even more long-lived. And they can serve as auxiliary qubits that have exhibited some really remarkable recent results coming out of Tim Tamanow's group at Delft. And just as there have been these remarkable advances in coupling the electronic spin of the NV to nearby nuclei, there have also been tremendous steps taken toward interfacing the NV electronic spin with photons that could comprise these flying qubits or communication channels. In particular, by exploiting the heralded entanglement techniques pioneered in the AMO community, NV centers have been entangled with the states of outgoing photons. Of course, you can do this for two different NV centers. And the quantum interference of indistinguishable photons from different NV centers enables entanglement generation between remote spins, heralded by photon detection. The essential idea here is that if the photons coming from the two NV centers are indistinguishable in every regard except for the degree of freedom that's entangled with their respective NV spin, then coincidence detection of the photons projects the NV centers onto an entangled state. But really, it does rely on the indistinguishability of the photons that they emit. Now, notably, this type of heralded entanglement between NVs led to the first demonstration of violations of Bell's inequalities while simultaneously closing the causality and measurement loopholes, which was really a result that put NV centers on the map in terms of a competitive system for quantum networks. However, the efficiency of such protocols is rather low in current experiments, with results coming out of the Delft group, which has really led the way in these types of experiments, achieving entanglement rates of about 39 Hertz for low fidelity entanglement, just barely above the classical limit, and for high fidelity to entanglement sufficient to, for example, violate Bell's inequalities, the rates plummet dramatically to a few per hour. So the motivation for the work I'll be telling you about is really trying to mitigate this inefficiency. And in order to explain to you how we mitigate this inefficiency, I should first explain to you where it comes from. And in order to do that, I need to tell you a little bit about the optical transitions of the NV center at low temperature. So throughout my talk today, I'll be assuming that we're able to work at cryogenic temperatures where the optical transitions of the NVs are not significantly thermally broadened. And even in this low temperature regime, if we put our NV center into its excited state, here I've just tried to draw the level structure of the NV, illustrating the spin 1 ground state and the spin 1 orbital doublet excited state. We put it in its excited state, for example, by exciting with green light to one of the vibronic sidebands, and look at the fluorescence that it emits. We see a sharp zero phonon line around 637 nanometers, and then a broad phonon sideband involving emission of both a photon and a phonon as the NV center relaxes. For quantum information purposes, it's only the zero phonon line that's useful, because photons emitted on the zero phonon line leave witch path information in crystal vibrations. Essentially, your photons cannot be indistinguishable because they're entangled with the vibration of the crystal. Now, within the zero phonon line, the NV center exhibits a fine structure that we can probe with photoluminescence excitation spectroscopy, essentially sweeping our excitation laser over the fine structure of the NV and looking at the fluorescence that emerges. And this shows a series of narrow spin-selective transitions that are reminiscent for what you might see from single atoms or ions. And so this looks very promising in terms of an optical transition structure. However, that zero phonon line where these nice transitions appear, it only comprises about 3% of the emission. And furthermore, while there have been occasional experiments that have revealed lifetime broadened lines in NV centers, that is extraordinarily rare. And in typical samples, the line widths that you see are substantially broadened relative to the lifetime limit. So in protocols where you actually need indistinguishable photons, if you have these broadened lines, you have to restrict the time at which you detect the photons to an interval that's approximately 1 over the line width. That is much less than the lifetime. So only a small fraction of your photons are actually useful. And this really explains what the inefficiency is coming from. First, we have only a small fraction of coherent photons in the zero phonon line, and then with time gating, we can only use yet a small fraction of those. And this becomes a really big problem, especially in high fidelity protocols that require 2 photon detection events. So if we want to enhance the rate at which we can distribute an entanglement across a quantum network, we need to, well, first we'd like to collect all the photons, but beyond that, we need to increase the fraction of light that's going into the zero phonon line. And ideally, we'd also like to decrease the radiative lifetime to get closer to the limit of actually extracting indistinguishable photons from our NVs. Cavity quantum electrodynamics is the paradigmatic solution to these problems. By confining an emitter such as an NV center in the antinode of an optical cavity, its emission rate on resonance with the cavity frequency can be enhanced by the Purcell factor. Essentially, the idea is if I tune my cavity resonance to the zero phonon line, then I can selectively enhance the zero phonon line at the expense of the phonon sideband. Furthermore, if I can enhance the rate of emission into the cavity mode sufficiently that I actually decrease the lifetime of my defect, then I can even move towards extracting indistinguishable photons. Now, this Purcell factor, it scales as the quality factor of the cavity over its mode volume. And this inverse relationship with mode volume motivated the development of high quality factor, low mode volume optical resonators made of diamond, such as this photonic crystal cavity and ring resonator that were made in the HP group nearly a decade ago. And this really looked like a very promising direction, at least initially. But there's an issue that comes into play here. And if there weren't this issue, I wouldn't be giving this talk. To understand this issue, it's helpful to get back to basic cavity quantum electrodynamics and consider our figure of merit for the probability of extracting an indistinguishable photon from our emitter. This is essentially given by the cooperativity, which depends on the Purcell factor, that is, the factor by which emission on resonance with the cavity is enhanced, and then this ratio of rates describing how bad our emitter is. Here, gamma ZPL, that's describing the rate of emission on the desired transition, the one that we want to collect. And on the denominator are all the bad rates. So we have the rate of emission into our phonon sideband. We have any non-radiative emission, which in the case of the NV center is pretty insignificant, but can be important in other contexts. And then we have pure dephasing on the optical transition. You can think of this as the frequency of the transition wandering around in time, potentially on fast timescales, potentially on slow timescales. And this optical dephasing rate is really the reason why this initial effort at developing diamond nanophotonics ended up being very problematic. Because when you put an NV center in proximity to these nanofabricated surfaces, the optical dephasing rate goes way up. Essentially, the NV center has no inversion symmetry, and so that means it has a permanent electric dipole moment, which makes it exquisitely sensitive to electric noise associated with charge traps on uncontrolled surfaces. Down to the 100 nanometer single electron moving around can significantly affect the location of your line. Now, the noise in the NV center optical transition commonly takes the form of spectral diffusion, which is basically the picture that the frequency of the transition is wandering around in time. And I'll distinguish between slow changes in the frequency and the single scan line width, which can play different roles. So, okay, but this is the issue. When you put defects into these nanofabricated devices, their line widths go way up. And if we want to overcome this issue, there's a few different approaches that you could take. So one approach is to do the material science and figure out how to improve the control over nearby surfaces. There's some really important work going on in this direction, for example, in Nathalie de Leon's group in Princeton, but it's highly challenging. Another option is to stop using NV centers. So by working with silicon vacancy centers, which have inversion symmetry and thus an insensitivity to first order to electric noise, the Harvard group has been able to make some really truly fantastic progress. They've achieved cavity quantum electrodynamic systems with cooperativity in excess of 100. With some recent results this year showing memory-enhanced quantum communications using this platform. So this is really a remarkable direction, a remarkable set of results, but it does come at a cost. The silicon vacancy has a poor spin coherence in comparison to the NV center unless you go to dilution refrigerator temperatures. And so these experiments require a bit of heroicism in terms of being able to put optical systems, optical devices into a dilution refrigerator. And so we were trying to find a simpler approach back when we were looking at this problem for the first time back in 2012. And our approach was instead to look at what we could do while avoiding nanofabrication. Could we use a relatively big chunk of diamond in some sort of optical resonator? And if we want to think about integrating a relatively large chunk of diamond into an optical cavity, we can return to the original picture of cavity quantum electrodynamics, where the optical resonator is formed by an external cavity. In this situation, the quality factor and the mode volume are less fundamental quantities than how good your mirrors are. Basically, I can change both the mode volume and the quality factor by changing the spacing between my mirrors. And how good your mirrors are, well, that's essentially their finesse, which is proportional to the number of round trips that a photon can make in your cavity before escaping. So the finesse is one of the fundamental factors that we'll have to consider, and also how tightly focused the cavity mode is, which I'll characterize with the cavity waist omega naught. So if I rewrite my Purcell enhancement in terms of these quantities, it becomes apparent that the length of the cavity drops out. The length of the cavity could be relatively large. I could think about sticking a several microns thick chunk of diamond into this cavity. I don't want to work with a macroscopic scale cavity because the line widths end up getting to be really too narrow compared to the lifetime broadened line width of the NV. And ultimately, the geometry that we settled on was one that was pioneered by Jakob Reichel's group in Paris, where we used one mirror that was fabricated on the tip of an optical fiber. This optical fiber has a small radius of curvature feature in the middle, which allows us because it has a small radius of curvature, it allows us to achieve a very narrow cavity waist. And there's been, again, many groups around the world using these types of cavities, both with solid state and with AMO systems. The geometry that we're pursuing is to use one curved fiber mirror and one flat mirror, where we bond the membrane to the flat mirror and then take advantage of the possibility for both spectral and spatial tunability to maximize overlap with the zero phonon line transition of a single NV in our membrane. Excuse me, I should have brought some water. In collaboration with the Sankey group at McGill, we've built a laser ablation system to fabricate small radius of curvature mirror substrates on the tips of optical fibers. This is now a pretty standard fabrication technique. Essentially, a pulse of CO2 laser light ablates a small Gaussian-shaped dimple in the tip of the fiber. This is an interferometric image of the tip of a fiber where you can see the dimple. And remarkably, this process also causes a reflow, a melting of the surface that leaves you with a near atomically smooth substrate compatible with state-of-the-art mirror coatings. Excuse me. And I should say we measure 0.2 nanometer roughness, but that's actually instrument limited. I'm not entirely sure quite how smooth it is. We can then assemble our cavities, again, with our fiber mirror and our mirror flat. We've been aiming for a design finesse of about 30,000, which our current coatings readily achieve. And then we introduce a diamond membrane into our system. Now, I should mention at this point that several other groups, including David Hunger, Christoph Becher, and Jason Smith, have done some very nice work coupling these fiber-based microcavities to defects in nanodiamond. Our focus, however, is to introduce a minimally fabricated, few microns thick diamond membrane where we can see narrow optical transitions of NVs. And you might be able to see in this image, there is a diamond membrane that's bonded to the flat mirror. The way we do that is really very easy. We float the membrane on a drop of water and we drag the water onto the mirror surface where, when the water evaporates, the membrane bonds via van der Waals forces. And if you compare this approach to what is required to, for example, confine a neutral atom or ion within a cavity, it looks just extraordinarily simple. But there's some important challenges that we've encountered here. I would identify three as being the ones that have really been the things that the field has had to grapple with as we move forward. And the first challenge is, of course, getting the whole reason of working with the system, actually achieving narrow line widths for NV centers and membranes. But we also need to worry about whether the presence of the membrane is going to destroy our cavity finesse. And then finally, we need to stabilize these cavities at the picometer level in a cryogenic environment in order to take advantage of the high finesse that can be available. So let's start with this first challenge. The first question is really whether our idea of retaining bulk-like NV properties in a few microns thick membrane even makes any sense. One of the first things that we did at McGill was to learn how to fabricate such membranes and study their line widths, comparing implanted samples to electron-irradiated samples. This is one of our electron-irradiated membranes. We shared our results and samples with the Delft group who are also interested in this question, and some of the measurements that they did on our irradiated samples showed line widths as low as 25 megahertz for a single scan. So that's at an instant in time. And I should say that we really found that electron irradiation works a lot better than implantation for getting the narrowest line widths, essentially by reducing the damage to the crystal. Excuse me. You'll notice here that I've given two numbers for the line widths, and it's probably not obvious to you if these are good numbers, if they are what you should be comparing them to. So you should be comparing them to the lifetime limit for NVs, which is around 13 megahertz. And these two different numbers tell you two different things. So if you're a theorist, look at that single scan line width. That's telling you at an instant in time, what is the line width of my NV center? You could use to calculate what the cooperativity would be if at that instant in time you manage to get your cavity on resonance with your NV center and that the NV center was at the transition frequency you wanted for your protocol. If you're an experimentalist, on the other hand, you might want to look at this spectral diffusion number as well. That's telling you about the slow changes in the NV transition frequency, notably when you apply a green laser to repump the NV into its desired charge state. And so the spectral diffusion is telling you about how difficult it is to get the NV center to the transition frequency that you want. And ultimately, both of these numbers will come into play for determining the efficiency of protocols. What's worth really underlying here is that these numbers that we were seeing in electron-irradiated and annealed membranes were very comparable to results that we saw in electronic grade samples. Okay. The Delft group later published a more in-depth study where they examined line width as a function of depth of the NV from surfaces, both for the spectral diffusion data here. This is as a function of, sorry, this should be in microns. That got cut off. So this is the membrane or the diamond NV depth in microns. Both the spectral diffusion line width and the dephasing line width or single scan line width maintained their bulk-like values down to distances around a few microns, down to about 3 microns or so. And so this is a really promising result. This is, for comparison, the lifetime limit for the line width. And this verifies the whole idea of doing this in the first place, that indeed we can see very, very nice line widths. I see there's a question.
Yep.
Yes.
So
the time scale for spectral diffusion. So this depends on the sample that you're looking at. In the nicest samples, the spectral diffusion happens quite slowly unless you turn on green light. And so what's happening when you illuminate the system with green light is you're basically exciting a bunch of other defects in the system that leads to a change in the configuration of essentially charge noise in the vicinity of the NV that changes the effective electric field at the location of the NV and causes the line to move around. And so what you'll typically see with the line shapes for NVs is that they're at one frequency and then you apply a pulse of green light and they jump to another frequency. And so when I talk about a spectral diffusion broadened line width, I'm talking about when I apply green light, how far does the line wander around? If you're looking at room temperature, you'll have very, very fast spectral diffusion. And if you have samples where you have a lot of electrical noise in the sample, even without this green laser intervention, you can see a faster spectral diffusion as well. So another question is asking what creates the spectral diffusion in your system. So I don't know the exact details of what's happening on the surface of these samples. The basic picture is that there's some charge traps where optical illumination can ionize the charge traps and cause the charges to move around and change the electric field. One potential culprit would be nitrogen impurities in the diamond. Okay. Thanks for the questions. And I should say, please feel free to ask other ones. So this at least indicates that we can get decent NV properties in membranes. But we're not getting down to the lifetime limit. There still is some residual spectral diffusion comparable to what we see in typical electronic grade bulk samples. The next challenge that I highlighted was the membrane losses, because of course none of this will work if the diamond membrane ruins the finesse of the cavity. While you might worry about bulk optical absorption, in the ultra-high purity electronic grade samples now available, for a few microns thickness, the bulk absorption is negligible compared to typical losses of the mirrors. Of bigger concern is the surface roughness, since scattering can also introduce losses. Excuse me. However, even as we were starting, there were results coming out of, for example, Anya Blazinski-Jajich's group at UCSB, where they'd been able to obtain surface roughnesses as low as 0.2 nanometers RMS using an argon chloride etch. And if I were just to estimate the kind of losses from reflecting off of a surface with that kind of surface roughness, it would be much, much less than the typical mirror transmissions that we're using for a finesse 30,000 cavity. And so while surface roughness is definitely going to be present, with appropriate etching techniques, we can get it down to a level that we can really live with. What we seem to be finding in our studies is actually that membrane loss is present, and it's limited by another non-roughness source of surface absorption or contamination, which typically limits our finesse to about 10,000 to 30,000, depending on the situation. And to explain to you how we've come to this conclusion, I need to explain to you how we can distinguish bulk losses from surface losses in our cavities. And to do that, I need to discuss the structure of the optical modes within these cavities. So a simple 1D model of the cavity mode produces a picture of the electric field inside the cavity that can look something like this. In this particular example, so the red is meant to be an illustration of the electric field amplitude within the cavity, and I've illustrated the two mirrors and the air diamond interface. In this particular example, I've chosen a resonant wavelength such that 6 3/4 wavelengths fit inside the diamond, which means that there's an antinode at the diamond surface. This makes this type of mode much more lossy, since the system is particularly sensitive to any absorption or scattering that's happening at the air diamond interface. In contrast, if I adjust the diamond thickness or the resonant wavelength such that exactly, for example, 7 wavelengths fit inside the diamond, then there's a node at the air diamond interface, and we have a mode that will suffer significantly less from surface losses. You'll notice that there's another difference between these modes as well. Unfortunately, the higher finesse mode types correspond to a situation where the field is mostly confined within the air, what I'll call an air-like mode. Whereas the modes that are sensitive to surface loss correspond to diamond-like modes, where, as would be desired for maximizing the Purcell enhancement, most of the energy is in the diamond region. And here I have illustrated a numerical simulation of one of the early systems that we worked with, where we had a fair amount of surface loss, to show you how the different types of losses in the system conspire to change the finesse as a function of whether you're in an air-like mode or a diamond-like mode. And notably, so in red here is kind of a best guess for what our system parameters had been in these numerical simulations, where we saw a finesse of 17,000 when we were in air-like mode, but when we went to a diamond-like mode, we actually couldn't see resonances at all experimentally. And this was very close to the type of behavior you would expect from having all of the losses localized at the diamond air interface, whereas other types of losses would lead to changes in finesse, but nothing like what we observed. Excuse me. Here we go. More recently, we've developed, is there a question?
Yep, there is a quick question, which is just, what is the typical depth of the dimple on your fiber?
Okay. So the depth of the dimple, I'd say typically is of order a micron. It depends on the radius of curvature. Typically, if we have a smaller radius of curvature, we'll have a slightly deeper dimple because it tends to drill down into the diamond a bit, although there are some other types of techniques that people have developed beyond just CO2 laser ablation to get shallower dimples. We're typically working with, we'd say 3 to 4 micron diamond membranes would be the ideal thickness to be working with. So having an extra micron of depth in the cavity doesn't make a huge difference. Excuse me. So we've been able to actually use our understanding of the modes to fit for surface losses expressed as equivalent roughness by taking data as a function of wavelength in different types of air-like or diamond-like modes. And with some improved etching techniques, where we add in an oxygen etch as well as the argon chloride etch, we've been able to reduce the surface losses to a pretty acceptable level. You'll note the irony here. We set out to avoid doing material science and surface science. That's what we've ended up having to do to try to reduce these losses. But it's worth noting that we're still in the regime where the equivalent surface loss that we're seeing far exceeds what we measure with our AFM, which does indicate there's some other sort of surface absorption and contamination. But at the moment, we can see finesse greater than 10,000 in diamond-like modes, at least in some situations where we don't have extra contamination in our system. And it's good enough that we can actually move forward to start to examine the coupling efficiency between defects in our membranes and our cavities. Okay, sorry. I should have gotten a glass of water. I wasn't thinking ahead of time. So we've done some experiments recently at room temperature to quantify the degree of coupling we can see between our defects and our cavities. And these are very similar to experiments that were done several years ago for example, this is a figure from Christoph Becker's group where they were coupling nanodiamonds, so NVs or other types of NVs and nanodiamonds to microcavities at room temperature, where it doesn't really matter that in a nanodiamond, the optical properties are not terribly great. So these types of experiments at room temperature are conducted in the so-called bad emitter regime of cavity quantum electrodynamics, where the emitter line width is hugely broadened. So here in red, this is the emitter line width at room temperature, which is for the NV, 100 nanometers wide, including the phonon sideband. It's very wide relative to the cavity line width. And the idea here is that you could use this as a tunable source of single photons by tuning the frequency of the cavity relative within the emitter bandwidth. And the presence of the cavity can enhance emission resonant to the cavity and thereby produce a flux of single photons with narrow line width and a greater spectral density that could be obtained simply by filtering the emission coming from the defect center. A common figure of merit is the fraction of emission, of photon emission into the cavity, which scales essentially as 1 over the mode volume. So actually, from this perspective, the types of membrane and cavity systems that we're working with are not ideal for developing tunable single photon sources, simply because we cannot get a very high fraction into fraction of photons emitted into our cavity with the relatively large mode volumes that we're working with. But nevertheless, by quantifying this room temperature cavity funneling into our cavity, we can actually quantify the degree of coupling that we're seeing between defects in our cavities. I see another, okay, so there's some questions about post-annealing processing. Yeah, we're doing regular triacid cleaning, which should hopefully produce a mostly oxygen-terminated surface. We have not done additional oxygen annealing. That's something that we could try to improve the surface properties of these systems. So post-annealing, we are triacid cleaning, but we don't do any further processing after doing well, we do have to, I guess we have to boil them in piranha in order to get them off the substrates after we have done the oxygen etch. And regarding degrading or improving over time, this is a little bit challenging to answer because we do see a lot of variability over our sample surfaces. So we would have to find the same region in our sample at different times in order to give and be very confident that we're at exactly the same region to be very sure that we're seeing a degradation in the quality of the sample rather than just being on a different part of the sample. So I can't confidently say that. I would say certainly over the course of many months, it's stable. I don't have data over many years at this point. Okay. So we've been able to quantify the coupling to our cavities at room temperature. And at room temperature, we decided to work with germanium vacancy defects, which have a narrower emission line than NVs at room temperature. That just makes the experiments a little bit easier. And I should emphasize this is a collaboration with Ulrich Anderson's group at DTU, who's interested in using GEVs for quantum optics experiments. So the way that our experiment proceeded here was that we had a diamond membrane with GeV defects in it bonded to our flat mirror, and we could characterize the defects in our membrane using a standard confocal setup where we're looking at the fluorescence of the GeVs with a microscope objective. Basically scan our sample between the excitation laser here and our collection optics and look at each point on the sample. So that was a confocal characterization that allowed us to identify single defects. And then we could replace the objective with a microcavity. And at each location on our sample, we would scan the length of our cavity, which would bring the cavity in and out of resonance with the broad emission of the GeVs at room temperature. So we would see a signal that depends on the cavity length, where we have lots of photons when we're on resonance and not so many when we're off. And then at each point on our sample, we would perform this sort of scan and plot the amplitude of the peak in fluorescence that we see as a function of position. So when we do this sort of comparison, we can use our confocal scan again to identify individual defects. And then this is our three-dimensional cavity scan with contours from the confocal scan overlaid so that we can identify the same defect and quantify with a lot of very careful calibration, the fraction of emission that's going into our cavity mode. And from that, we were able to estimate that we were seeing a per cell enhancement of approximately 30. But perhaps most importantly, this experiment demonstrates the quality of the samples that we've been able to obtain. In particular, it was the first time that coupling of a defect to a diamond-like mode has been observed, in this case retaining a finesse in excess of 10,000, even with an antinode at both diamond surfaces because of the choice of mirrors that we've made. And so the obvious next step is to cool our system down to the point where the emitter line widths start to approach the nice results we've seen before in these membranes. But it turns out this is not as easy as it sounds. Cooling down is hard because we need to maintain tunability in our system. We need to be able to search for a low-loss diamond-like mode. We also need to find a defect center with excellent optical properties. But at the same time, we need to stabilize our cavity on resonance with the defect transition, that is, locking it within a few picometers. And we need to do this on top of a floppy translation stage in the presence of cryostat noise. Now, in the years since we started working on this, back in 2014, 2015, there's been considerable progress around the world in engineering such systems. The most obvious approach is to use a bath cryostat, which should minimize the external noise on the system. And some of the nicest results have been achieved in Richard Warburton's group, where in a collaboration with Patrick Malatinsky, they cooled down a diamond membrane in a microcavity in a bath cryostat. And by placing their bath cryostat in acoustic shielding and on an active vibration canceling platform, they were able to achieve a passive stability of about 24 picometers RMS for their cavity length. In case those numbers don't mean much to you, they correspond to a finesse of about 13,000. And I should mention that there's many other groups that have been doing things like this. For example, Valid Sandogdar's group achieved similar levels of stability in a bath cryostat by employing active cavity locking. Now, this Malatinsky-Warburton collaboration was able to demonstrate coupling to several NVs within their cavity mode. While they were limited by membrane losses to a finesse of about 5,000 in an air-like mode, their small radius of curvature cavity achieved a per cell enhancement in the range of 30, which was a beautiful, beautiful first step. However, the significant dephasing that they had in their samples meant that this only corresponded to a cooperativity of about 3%, so very far from the strong coupling regime. For us, a bath cryostat with concomitant helium costs was just completely out of the question. So from the get-go, we've been working with a closed cycle cryostat. And using a closed cycle cryostat for this might sound like the epitome of madness, but actually there have been many groups that have been successful in getting some very good vibration stability, even in a noisy closed cycle system. So I'd like to mention a couple of recent results that came out on the archive this year. For example, there was a collaboration between David Hunger and Hugues de Riedmetten, who are using the Colibri platform with active cavity locking, where they were able to, so I say they were working with erbium ions, where they had a narrow cavity resonance. And using side of fringe locking at 790 nanometers, where they were able to achieve about 20 picometer RMS motion during quiet times, which is quite comparable to what you can get in a bath cryostat. Excuse me. The Delft group, using the same kind of Montana Instruments cryostat that we use, was able to see passive stability down to about 50 picometers RMS using a commercially available vibration isolation platform. And furthermore, they were able to see a Purcell enhancement of about 4 for single resonantly excited NVs in their cavity, limited primarily by vibrations in their system. So when they were actually taking data, they ended up with about 200 picometer RMS worth of vibration. So you might notice that even with worse vibrations, they achieved a similar cooperativity to the previous results. And that's really because the line width of their NVs was an order of magnitude smaller than before. And so this creates a lot of hope that if you can combine low vibrations with narrow line widths and small membrane losses, that you can start to push, you can get another, at least one more order of magnitude and start to push towards the strong coupling regime. So while we certainly have a lot of company in building these systems, I hope this background gives you some context, since I'd like to tell you a bit about the system that we've built. The system we're building is based on a customized Montana Instruments nanoscale workstation containing a custom-built 3-axis scanning stage from JPE. So these knobs here that you see, those are piezo knobs that cause tip and tilt of a platform that in turn supports our flat mirror, so that as they tip and tilt, this pillar moves back and forth and scans our flat mirror and sample relative to the fiber that forms the cavity mode and our excitation light. Excuse me. The parallel kinematics of this design permits a high first resonance frequency of around 3 or 4 kilohertz, which helps to suppress the impact of low frequency cavity noise, low frequency noise on the cavity. Excuse me, I really should have gotten some water. The stage is mounted within a home-built vibration isolation platform. So that's this thing that you see around it, that was designed to suppress noise above its roughly 100 hertz resonance frequencies by at least 40 dB and as much as 60 dB over much of the relevant frequency range. So this is basically saying, how much do we expect our cavity to vibrate relative to the vibrations that are actually moving our cold plate up and down. Even with this vibration isolation in place, we're also exploring active stabilization, because ultimately we'd like to get down to picometer level stability that would let us pursue high cooperativity systems. And for cavity locking, this has some advantages because the shear piezo that our fiber mirror is mounted on has a very high resonance frequency, and the fiber mirror is very lightweight, so it has low inertia and can respond rapidly even to high frequency components of the vibrations, ideally leading to a tight lock. So this is an image of our fiber mounted on the shear piezo underneath the flat mirror here. However, we do have to contend with the somewhat floppy nature of mounting our system on a 3-axis stage and the considerable noise of our cryostat. So I'd like to share with you some of our recent unpublished results on the performance of this system. To lock the cavity, we use the Poundrever-Hall scheme to generate an error signal. If you haven't heard of PDH locking before, basically you can think of it as dithering the laser frequency and measuring a lock-in signal that effectively gives you the derivative of the cavity resonance line shape as your error signal. And that gives you something that's linear in the displacement around resonance that can be fed back to the high-frequency shear piezo to stabilize the length of the cavity. This error signal also gives us a way to measure the displacement of the cavity from resonance while locked or unlocked. Again, it has this linear behavior around resonance that we can use to detect the cavity length. And when we have our compressor off, we have a really beautiful, excellent lock. And in fact, if I zoom in here, you can see it's dominated by electronic bit noise from our scope. So we're really locked very, very tightly. However, when we turn the cryostat on, it is an entirely different story. So hopefully already this comparison illustrates for you the challenge of stabilizing a high finesse cavity in a closed cycle cryostat. This is data for our cavity locked at room temperature. And as you can see, even while locked, the error signal is going pretty wild. And notably, it doesn't stay in this linear regime, making it more challenging to infer the actual length excursions of the cavity. Excuse me. However, if we can monitor both the transmission and the error signal, then we can in fact determine the length of the cavity unambiguously. So to explain how that works, which is the way that we characterize our vibrations, I'm showing you here both the error signal, which is basically we're close to resonance and things are drifting around. So we're seeing our error signal going up and down, and our transmission. So we're close to resonance, but it's drifting around. So we see it falling down from the maximum transmission value. I'm showing you these as a function of time. And as you can see, there are excursions that take the cavity out of resonance, but they're still within the capture range of our lock. So to illustrate how we use this data to infer the length of our cavities, I've plotted the transmission and error signal values parametrically for this data set and compared it to a scaled fit of the calibration here that has a known cavity length as its x-axis. And so the idea is that basically at any instant in time, I have some transmission and error signal value that corresponds to a point on this graph. And if I can figure out the point on the blue line that it corresponds to, then I can extract the length of our cavity. So using this parametric technique, we've been able to measure the vibrations of our cavity, both at room temperature and at low temperature. And our results, honestly, were kind of surprising to us. The first surprise was that when cold, our cryostat produced much less mechanical noise than it did at room temperature. So what this data is showing you is showing the RMS vibrations as a function of time at low temperature. And the total RMS vibrations that we're seeing on average at low temperature is about 60 picometers RMS, whereas when unlocked at room temperature, we were seeing close to a nanometer RMS worth of motion. Okay. The two curves that I'm showing you in this graph correspond to the RMS motion that we see when we're unlocked in red and when we're locked in blue. And that was surprise number 2. While locking reduced our noise by 2 orders of magnitude at room temperature, it did almost nothing for us at low temperature. Fortunately, if I zoom in on the quiet periods that are synchronized to our cold head, so basically the low noise periods in each cycle, we see that the cumulative RMS motion is only 60 picometers even when unlocked. And while we don't gain very much with locking at low temperature, if you're curious why, I can answer those questions maybe at the end. Nevertheless, even without locking, we have sufficient vibration stability to really move forward. And so in some ways, even though the work we put into developing a nice lock at room temperature didn't pay off at low temperature, this is good news in that we don't have to lock in order to move on. So since our passive stability, especially during the quiet times, is better than expected, good enough to work with finesse 20,000 cavities, we're in the process of running some experiments with the same GeV sample that we've already characterized at room temperature. And actually our vibrations are now good enough that we're back to being limited by surface losses in our membranes rather than vibrations. Moreover, our initial characterization has given us tools for improving our cavity lock at cryogenic temperatures. And ultimately, if we can get yet better membranes in terms of systematically understanding the loss mechanisms and exploring mitigation approaches, it looks like we can at least start to push the boundary towards demonstrating strong coupling to NV centers. Okay, I'm almost out of time, but I wanted to, in the last 5 minutes or so, take the chance to advertise another system that we're working on in my group, which also uses NV centers, but in all other regards is quite different. Our goal here is to use NV centers to probe the dynamics of spin transfer driven nanomagnetic devices. Let me parse that for you a little bit. Essentially, the idea is that we can use the spin of the NV center, even at room temperature, as a sensor for high frequency magnetic noise. Essentially, the idea is that the NV center spin will relax in the presence of noise that is resonant with either of the transitions between its Zeeman sublevels. I should emphasize that here I'm talking about spin sublevels, and I'm talking about spin sublevels that are highly coherent even at room temperature, so we don't need a cryogenic system for these experiments. This gives us a spectrally selective probe of the magnetic field because these relaxation rates depend on the noise spectral density of the magnetic field at the spin transition frequencies, which then allow us to look at the high frequency dynamics of a proximal nanomagnet. So this illustration here is showing you a chunk of diamond that has black spins that are meant to represent NV centers that we probe optically to gain information about the dynamics of this blue magnetic layer. Now, the other half of our title is talking about the idea that we're interested in using the NV to examine dynamics that are controlled by spin transfer effects. So what is spin transfer? The idea is that if we can inject spin currents into our magnetized layer, which in this geometry we do using the spin Hall effect, those spin currents can exert a torque on the magnetized layer that tends to tug the magnetized layer in the direction of the spin polarization. In the work I'll mention today, we're particularly interested in probing the effects of DC spin currents, where injecting a spin parallel to the magnetization will tend to damp out any thermal oscillations of the magnetization. And forgive my poor PowerPoint illustrations here, but that's the idea. While injecting a spin anti-parallel will anti-damp thermal fluctuations, and in some geometries can even lead to spontaneous auto-oscillations of the magnet. Again, forgive my poor PowerPoint illustration. Jack Sankey, who's my collaborator on this project, likes to call these flute dynamics in comparison to the way that a DC breath blown into a flute can excite sound waves. So there's a bunch of different ways that we can explore measuring the damping and anti-damping effects of DC spin currents on our magnetization. One of them is to look at how anti-damping can enhance the amplitude of parametrically driven ferromagnetic resonance. The idea is that if we tickle our nanomagnet with a parametric drive at twice or close to twice its FMR frequency, and then anti-damp with spin currents that are anti-parallel to the magnetization to enhance its response, then we can detect the resulting magnetic noise with an NV sensor whose spin transition frequency is tuned close to the FMR frequency without having the spin transition frequency affected by the drive at 2F. Here, for example, I'm showing the fluorescence of an NV center as we vary the frequency of the paramagnetic drive around twice the NV transition frequency while increasing the anti-damping to the magnet. The strong NV response in the presence of anti-damping, so the fluorescence goes down when there's magnetic noise resonant with the spin transition. It indicates that we're getting to very large angle precession enhanced by anti-damping, and it illustrates how we can use an NV center as a local probe of spin transfer effects. We can map out this response to parametric driving over a range of magnetic fields and frequencies. So this is a transport measurement that shows us where parametric driving is effective, showing us twice the FMR frequency effectively with contours on top of our NV fluorescence plot. These 4 dark lines are very boring. They're just the NV spin transitions being driven directly by the parametric drive. The interesting part is up here, where we're seeing the NV spin transition being driven by the precessing nanomagnet, which is itself driven parametrically at 2F. And notably, the NV measurement reveals a strong response outside of the regions observed in transport and may also show some evidence of bistable behavior. I see a question. Okay, how large of a region / ensemble is this data? So this is actually a single NV center. Thank you. Yeah, it's very helpful to work with a single NV center because the magnetic field gradients in proximity of these nanomagnets are extremely large. And so you get quite a bit of inhomogeneity of response for different NV centers around the nanomagnet. Okay. Going on. We can also look at what damping and anti-damping does to the thermal or undriven noise from the magnet. Oh, sorry, Thaddeus, you're asking what is the distance from the NV to the magnet. We only have confocal data to go on. I would estimate 400 nanometers or so, order of magnitude, plus or minus 100 nanometers. We don't know it exactly. So that's made it very hard to simulate our system very precisely. So we can also look at what damping and anti-damping does to the undriven noise, just the thermal noise from the magnet. And essentially what we see is that the NV spin relaxation rates, which are proportional to the magnetic noise, increase with anti-damping and decrease with damping. And I don't have time to go into the details, but we've done some analysis modeling the system, trying to understand what would happen in the absence of spin transfer. This data was taken, trying to keep the FMR frequency constant. There's a lot of details that go into this, but essentially we come up with a theoretical prediction of what we would see in the absence of spin transfer effects, which leads us to believe that in the damping regime, we're seeing spin transfer cooling of the magnetic modes to an effective temperature of around 150 Kelvin. Excuse me. More recently, we have new devices that exhibit flute dynamics under DC anti-damping currents, where essentially we are sending in a large enough DC current to drive spontaneous oscillations of the magnet near 4 gigahertz. And when we tune the magnetic field to around 41 millitesla here, this 4 gigahertz oscillator becomes resonant with the ms equals 0 to ms equals +1 spin transition, which creates this dark vertical stripe. It's basically saying where things go dark, there's magnetic noise resonant with the NV spin transition. In this case, at 4 gigahertz, our spin torque oscillator is resonant with the ms equals 0 to ms equals 1 transition. Now, in addition to anti-damping and driving this spin torque oscillator, we are also applying a weak drive that, when the drive is near parametric resonance with the oscillator, can cause the oscillator to phase lock with the drive. And we see evidence of this phase locking in the regions where the oscillator is essentially pulled off resonance by the NV, by the weak drive that we're applying. There are even places where the large angle motion of the oscillator appears to change the effective magnetic field of the NV, thereby pulling its transition frequency away from the expected ms equals 0 to ms equals +1 parametric resonance here. We see some evidence of a second mode in our device. And there's even potentially some indications of power transfer from the spontaneously oscillating mode to the second mode. And the second mode has a frequency that changes with magnetic field. So at this point, we might actually be driving the second mode and sapping power. Now, this is all very preliminary data. We're spending a lot of time right now trying to make some sense of it and modeling our system, but it's an illustration of some of the rich features that we can see. We're also hoping to use the NV to probe the spin torque oscillator coherence and get some faster quantitative measurements of spin relaxation times with Bayesian estimation techniques. And ultimately, I hope this illustrates our interest in seeing what we can learn about spin transfer systems with this new type of local probe. So with that, I'd like to thank my group and my collaborators, particularly Yannick Fontana, who designed that vibration isolation stage, Erica Janetz, who really led the cavity coupling experiments, Rigel Zifkin and Cesar Rodriguez Rosenbluth, who are taking over our cryo system, and then Adrian Solium and Michael Cowett-Mansour, who've been working on our spin transfer project, as well as our collaborators, our funders, and of course you for your attention.
Thank you so much, Lily, for a great talk. I know I certainly appreciated your nice pedagogical explanation of everything. Do we have additional questions from anybody? Well then, if not, okay. If not, thank you so much for, oh, here we go. Oh.
Thanks, Thaddeus.
So we have from a former Bates undergrad, was asking when you were at Bates.
I was at Bates from 2007 through 2010.
Yeah. So, why doesn't locking make a difference when cold?
Okay, so these are the slides I left out. I have a very detailed answer to what goes wrong with locking at low temperature versus room temperature. So it gives me an excuse to go through what is so hard about locking at low temperature. Before I can really tell you what's hard about locking at low temperature, I should mention first that there's a lot of things that made it hard to lock at room temperature with a cold cycle cryostat running. And I'd say the three things that were really a problem. So one was the dynamic range or the width of the error signal. The idea is we have an error signal as a function of cavity length. And if the cavity length excursions are too large, we get out into a regime where there's essentially no restoring force. And so this dynamic range is something we had to spend a lot of time trying to maximize and involved, working at lower finesse, essentially to make that dynamic range larger. Another thing we did battle with is what's essentially fluctuations in the offset of our error signal that's caused by residual amplitude modulation present in our PDH locking system signal. And so what that does is basically it causes our error signal to go up and down in time. And if it fluctuates like this, then where it crosses zero here, you actually get into a regime of positive feedback. So if you have a length excursion that goes that far, it will immediately come unlocked. And so we had lots of issues with getting our lock to be stable. And we had to add in an additional feedback circuit to stabilize the RAM. Okay, the third thing that makes this hard is we need a high bandwidth lock. Our noise is predominantly in the kilohertz range because of the kilohertz frequencies for our translation stage. And at room temperature, this is a transfer function, open loop transfer function for our lock. If you don't know what that means, basically you can look at this magnitude. This is essentially the factor by which we can suppress noise in our system. And so the point at which we hit 1 is our bandwidth. And at room temperature, we could suppress noise up to about 10 kilohertz. And down at a few kilohertz where we had most of our noise, we had a pretty good noise suppression. When we went to low temperature, our bandwidth died. We had a bandwidth about 1 kilohertz. Our noise suppression at lower frequencies is concomitantly reduced by basically a factor of the square of the reduction in the bandwidth. And the fact that we have this lower noise suppression means that we again have issues with the dynamic range because we now have a larger set of excursions in our cavity mode. And so ultimately the problems are all coming down to the reduced bandwidth of our lock at low temperature, which looks like it's being suppressed, being limited by a resonance at around 10 kilohertz. We don't have a lot of great data on this because in order to take the lock transfer function at low temperature, we actually had to turn our compressor off. We had about 30 seconds before our system drifted out of range of our piezo, and then you can't repeat this process rapidly because of the limitations. Anyway, this was hard to get. So we don't have great data, but it looks like most likely we're being limited by the sharpening of a resonance at 10 kilohertz. This was present at room temperature, but it wasn't as sharp because the material damping properties get much, much lower as you go to low temperatures. And we've done some modeling that associates this with the tripod that's supporting our fiber mirror. And so we have some indications that the place where we need to improve our design is either somehow adding some damping. We already have magnetic damping and tuned mass damping present in our vibration isolation stage. Maybe we need to think about incorporating some sort of damping into the actual fiber support or making the system a little bit stiffer or more massive. So this is the long story for why we didn't see much of an improvement with locking at low temperature, but it does point towards some places for improvement.
That's really interesting. Yeah. So there is one more question: is that when you're locking, do you see polarization drift due to temperature fluctuations?
So we're fortunate in that the birefringence in our cavities is relatively low, and so we don't really need to worry about polarization. It is an issue with these systems because often due to strain in the diamond, you will see significant birefringence that would lead to basically two cavity modes that you address with different polarizations. We haven't seen that being a problem in this characterization. We didn't have any diamond present in our system. We just had a bare cavity for characterizing the vibrations, and so we didn't have issues with polarization. But that is something that you'll have to think about as well.
Well, thank you so much for an excellent talk. I'll clap even though you can only hear me. And thank you everybody for coming, and see everyone later.
All right. Thank you.